So I just started recording here, and I appreciate a student who just noted that I had not been recording. So far, all I've gone over is just a review of what is a model that we talked about from last lecture. I apologize for those of you tuning in asynchronously. And if you were to go through this lecture, which is stored online, then all you'd see is that I'm just going through the steps of saying from last time, we basically motivated the use of this word model. We talked about a model is globally just something that answers a what if question. And you can have animals that can be models for other animals, and you can even have humans that can be models for other humans. So that's kind of a recap of where we are so far. And sorry about that, I'll get better at making sure we're recording from the start from then on. All right, so what about this? Is this a model system? So what the heck are we looking at? This is a almost bird's eye view of a traffic intersection. So notice you've got cars coming in from at least 4 directions, and they're coming in here and there are no stoplights. There are crosswalks all over the place, and these cars come together, and strangely enough, they seem to form a type of traffic circle here. So maybe if it's hard to see, let me see if I can flip. So you can kind of, let me flip to a different tool here. All right, so you can kind of see that there is this circular flow. Oh, sorry, let me draw on this other screen. There is a circular flow here that is kind of naturally formed when all of these cars hit this intersection here, which I think was kind of surprising to me. So, so with that in mind, is this a model system? So, so does anybody have an argument either way here? Does anybody have something they'd like to share? When you're looking at this, this is a real intersection right there out there. This is not a test intersection. This is not in the laboratory somewhere. This is out there in the real world. Is this a model system?
I believe it is, because what if there is no stop signs or street lights in an intersection such as this? So they kind of want to see how it all plays out, and it seems to just form a circle on its own.
I think that's a really interesting way to put it, is that this is not an intentional experiment, but it just happened. And this is one of those things where if you're sitting at the pub or whatever, you know, in the before times or hopefully in the way after times, and you're chatting with somebody and saying, what if we had intersections that didn't have stoplights? And everybody could have a possible guess. There'd be collisions, you know, people would get run over, all of these different things. And then somebody then says, you know what, I was in India, this particular time, in this intersection, I happened to notice, or I was in Singapore, or what, wherever you happen to, and there was this weird, thing where this happened. Maybe the stoplights weren't working, or maybe it was intentionally engineered this way. And suddenly, so there's a comment in the chat, they need a roundabout. This sort of suggests that if we had a roundabout, it would help in this particular situation. But it sort of suggests that maybe they don't need a roundabout. Maybe the roundabout happens organically, just out of these cars coming together, and this due to people's natural inclination to go in one particular direction, and then kind of you get this circular flow. So I'm not saying this is the best way to build an intersection, but this phenomena is surprising to me. And usually when something is surprising, that indicates that you have inadvertently made use of a model and you have learned something about the world, and that is useful. And whenever you have learned something by using something else, then that's something else that has helped you do that, I argue, is probably a model. And so this is a model of an intersection without stoplights. Now, if you did this, say in the United States, it might not work. Just like you put that jacket, you take that jacket off the fashion model, you put it on me and it looks terrible. It doesn't always mean it's going to work, but it gives me confidence that maybe now we should try this in another area, in an intersection in the United States. So yeah, there's a comment in the chat. It comes naturally in their culture because it's something they're used to. So that's kind of an interesting point. The physiology of the mouse is close enough to my physiology that we can make some inferences when you experiment on the mouse about how it's going to react in me, but they're not perfect. The culture of a society is like the physiology of that society. When you go from one society to another, it's like you're flipping from slightly different physiologies. Their culture might be totally different. My father is an attorney, and they in law school used to talk about experiments that they used to run in the United States and in Mexico, where they would record people without those people knowing in basically in the middle of the desert with no other cars around except for one car and stoplights. And they would see how many people would stop at a red and wait for the red to turn green and how many people would go through. And there were significant cultural differences, is that in one particular culture, and I'll let you sort of, you can kind of think about how this, your guess as to which one's which, but in one particular culture, if nobody was around, they would stop briefly and then just go through the red light. And another one, then they would stop there and wait for the green. So the culture is really important to sort of understanding how these intersections work, for sure. But we still get, so models are never perfect, but we do learn something. And when the models fail to predict what actually happens in the system we're interested in, that tells us again about that system. Like Morgan mentioned in the chat, the culture might be different. So that tells me that this particular intervention will only work when coupled with this particular cultural norm. And another cultural norm, I might need a totally different intervention, and I might need a totally different model for that. All right, so similarly, if we're talking about models in the real world, this is the Titanic up here. So here's Kate and Leo down here. And, is this a model system? So, you could say that, I can't, this is a tragedy. How could I possibly call the Titanic a model? Well, like it or not, they learned a lot from the Titanic. There's still papers been written today about what happened to the Titanic. It wasn't just as simple as this boat ran into an iceberg, and it actually turns out that the metallurgy and everything, like the fact that they made the boat out of particular metals, it turns out that those metals get really, really brittle in really cold water, and that was something that they didn't know happened. And so the thing that they hit may not have actually been the we would picture this major, they ran into this giant thing that just would tear any boat apart. Well, it actually turns out that maybe they ran into something relatively benign to modern ships, but to this particular ship, because of the particular metal they used and the particular waters they used, was really brittle. And so engineering out there is experimentation. Whenever you implement something and deploy it onto a society, that society becomes unwitting participants in your experiment. And so if I was to do an experiment in my research laboratory using humans, I would need to have them sign off, giving their so-called informed consent. But the beauty about research in the real world outside of academia that's not funded by the government is that they don't require informed consent. And so whenever you get into a new car, whenever you get into an elevator, whenever you get into any new piece of technology, you're sitting in front of a computer screen that's powered by it has an AC adapter in the wall there that potentially could be could burst into flames at any moment. There is an experiment being run in which you are participating, and you probably have not given your informed consent. You are the lab rat or the lab mouse in this particular case here. And a wonderful example of this is one I used to teach an engineering ethics course, and we talked about this. There's a question here. Has anyone ever seen a model of how many different ways? So I'm not sure I understand this reference here.
They're talking about the characters in the movie.
Oh, gotcha. Right. Okay. Yes. So there you go. So that's so again, that's a what if question right there. So that's an excellent use of saying, like, whenever you're sort of saying, I don't know the answer to this, well, what if they were oriented in these different ways? How many ways could you do that? All right, so this ABS example, anti-lock braking system. So those of you who've driven I don't know, I have a model of how old most of you are, which is probably right for most of you, but wrong for a handful of you. But based on my mental model of how old most of you are, my guess is that most of you learned how to drive. Those of you who learned how to drive, know how to drive, on a car that has anti-lock braking. This is vehicles with anti-lock braking. Basically, there's brakes that grab the wheels. And in the old days, then when you put your foot on the brake, they just clamped down on the wheels. And that would create so-called locking conditions if you were going too fast, because your car, the wheels could start sliding. And once the wheels are sliding, then it doesn't matter how hard you're hitting that brake, because you're trying to slow the wheels down, but the wheels aren't moving with respect to your car anymore. They're moving with respect to the road, and that is out of your control now because you're sliding. So to prevent that, they engineered something that whenever they detect that this is about to occur, then the brakes pulse. And so any one of you who maybe when you're learning to drive or whatever, you might have taken your eyes off the road and you come back and you suddenly see a car in front of you and you slam on that brake, sometimes you'll hear a hum, and that hum is a pulsing of your brakes. And that is keeps a way of slowing your wheels down while preventing them from ever locking up and going into a slip condition. And so this ABS was, when it was originally deployed as a feature, so back in those days, you had to learn how to pump your own brakes. And so back before ABS, if you needed a hard stop, you had to, in the back of your head, say, don't just slam on the brakes, but lift up, and then you actually had to pulse your own brakes to prevent them from locking up. And so they said, we're going to do that for you. We're going to have an automated system do that for you. And people across the board said, there's no way that an automated system could do this better than I can. And so people were really critical, and they said, this is just going to cause me to get into more accidents, because the thing about anti-lock brakes is you do not pump anti-lock brakes. That's like the worst of both worlds. So you really have to trust the anti-lock brakes. People say, I don't trust it. I'm going to get into more collisions. And the weird thing is, people did get into more collisions. And so it turned out that after they deployed ABS, collisions went up. But the funny thing is that when people actually analyzed the crash data, the collisions were not front-end collisions. They were not the car with the ABS running into another car. They were rear-end collisions with the cars that had ABS. So when ABS trickled out, so few cars had ABS that the cars on the road that had ABS were stopping so fast that the cars that didn't have ABS, that were driven by humans, were running into those cars. So this is a technology that if everyone had the technology, everyone would be safer. But when you're the only one with ABS, you're actually less safe, because all of the people behind you are going to be hitting you because your car stops too fast. You're avoiding collisions with all the cars in front of you, but you're getting hit by all the cars behind you. So that kind of showed them that when you implement a technology like ABS, there needs to be a certain amount of market penetration to actually realize the benefits. And without that, then this can actually create a misconception about the safety of the technology itself. People thought the reason why people were getting into more collisions is that ABS was bad at its job. Turns out it was too good at its job. And so people had to update their mental models. And so that's what we do in modeling, is we come up with a guess for how things are going to work. We experiment with it. And then based on that experiment, we update that model, and we keep that going over and over again. And that continues when we actually do an intervention, when we implement the car, the windmill, whatever. That our implementation actually continues to be a model. And that's why our technology and our knowledge in general keeps getting better, because we keep learning, because everything we implement is a model for the thing that we're going to implement in the future. All right. So with that in mind, again, I want you to start adopting this more generous viewpoint of what models are. And so models don't have to be mathematical. They don't have to be a computer simulation. They can be pictures, for example. So on the left, we have a so-called beaver tail cloud formation. On the right, we have a so-called wall cloud. So these are two examples of clouds that have been named by meteorologists. And if I take the beaver tail, for example, and I look at all the rest of these, then I hope you can immediately see similarity there. I can show you a picture of a beaver tail cloud. I can tell you beaver tail cloud formation without the picture, and maybe you use those words to help you sort of understand what I'm thinking about. But once I show you that picture, then later on, if you see any of these, you're probably much more likely to say, ah, that's a beaver tail cloud formation, and that indicates, something about the weather. So, so this becomes a what if here of, what if there's a lot of different what ifs here. What if I see something like that? Well, if I see something like that, then that indicates these processes are going on behind the scenes. And so, this isn't exactly the same as this over here, but this picture here is pretty darn close. And so it gives me a good idea of what's going on there. And then, likewise, you can start seeing major differences here. So you can see that a funnel cloud, like here, that's different than this beaver tail. And a funnel cloud is a precursor. So here's a much larger funnel cloud. And so we can see that there's similarities between these, which maybe group them together. But there's also important differences in the meteorological processes and the ultimate consequences. So pictures can be models because they're communicating to us, useful ways to make inferences about the real world. So what's useful here is by looking at this picture, that helps me know that if I were to see any of these things in the real world, I can now make a useful inference about what's going on. Similarly, if I know what a funnel cloud is, if I see a funnel cloud, I can make a useful inference about what's going on and maybe get the heck out of there. Even the term funnel cloud, it combines funnel over here and cloud. A cloud doesn't look like a funnel. A funnel doesn't look like a cloud. I use those words together, funnel cloud, and you can in your mind picture, what a funnel cloud might look like. And so that ends up being a useful model. So what is your model for what the cloud formation that precedes the tornado looks like? Well, it kind of looks like a funnel, so, it's okay, it's a funnel cloud. That's my model for what the shape of this thing will be. What if we were about to get a tornado? Well, if we were about to get a tornado, then we would probably see a funnel cloud. So that's like even things like pictures and words can be models. Graphs can even be models. I already have shown this sort of graph where we've got predator and prey and going through these oscillations, and that helps me explain the way predator and prey can self-regulate each other in this kind of feedback cycle together without actually being real data. Real data itself, like these data points here, which are plotted between high school GPA and university GPA. If I just plot those data points, if I notice they have a particular shape, it shows me that there is a correlation between high school GPA and university GPA. I'm not saying what the causal factors of that is, but that allows me to sort of say that, oh, there is a link between there. So either high school GPA has something causally to do with university GPA, or there is a common cause for both of those to be linked together. And so it gives me useful and allows me to make useful inferences about the world. The line that goes up through here. So if I fit a regression line through these data points here, that line itself becomes a model, because that line says, regardless of what the causal factors are, if someone has a 4.0 high school GPA, they are pretty likely to have close to a 4.0 university GPA. So that answers a what if question. So this line suggests an answer to a bunch of what if questions. The next step is to go and test that model out with experiments in the real world. And then, down here, it doesn't have to be real data. So this is an example where it plotted exercise intensity on one axis and oxygen consumption on another. And these are not real data points. But the fact that I plotted little dots here makes me say, what if we did an experiment and plotted the data? The little dots here suggest that there's fictitious data that could be plotted here. It's kind of a what if, like, these are roughly where the data would fall. And the lines that connect those dots, this black line here that has a corner here, communicates a model of physiology that has this so-called VO2 max. This is a point where beneath that point, if you increase your exercise intensity, you'll increase your oxygen consumption. But supposedly this model of human physiology suggests that if you were to exercise really, really intensely, your body would cease to be able to increase its oxygen consumption. And that extra exercise intensity would have to be powered by anaerobic processes, so processes without oxygen. That's just a model of what somebody thinks the human or maybe the vertebrate physiology or maybe just animal physiology works, like how it works. We don't know that it actually works that way, but by drawing this graph, I've communicated to you how I think animal physiology works. So that's my model. What if an animal were driven to intense exercise intensity? And the claim is that, well, up to a certain point, their oxygen consumption would increase, and then they'd hit a point, and that special corner would be, we would call that VO2 max. And after that corner, their oxygen consumption wouldn't increase anymore. So the graph has communicated the model to me. So graphs can be models too. So I'm hoping here that it's sort of clear here what I mean by models answer what if questions. So with that in mind, let's do another sort of thought exercise. So there is this term model citizen. So in thinking about this what if question, where does that term come from? Does anybody have an idea of why we would call a model citizen a model citizen? Where's the model there?
Well, like you kind of like have like all the qualities of a citizen that people should strive to be, I guess.
Okay, so that's interesting.
Politicians too.
Like you're like an example.
Sorry to interrupt you. If you wanted to
that's
keep
great.
talking.
No, you're good. You're good.
Okay. I don't know. I kind of got the feeling that it comes from people who are, a lot of times this comes back in history, like people, philosophers like Socrates or etc. It comes from a lot of like history and led by example, exactly. Kind of like people who think they had those qualities and then it changes through generations, but that might be where it comes from.
Interesting. So I've seen in the chat lead by example, and that was also Morgan, referenced that as well. And yeah, so so far, it sounds like we've said that a model citizen is somehow a caricature almost of how a certain group of people think other people should behave. So, I think the example there was a politician. A politician maybe doesn't have to wear a mask, but some people might say that even though the politician isn't compelled by law to wear a mask during COVID, the politician should wear a mask during COVID because they are modeling appropriate behavior. Not, not, in other words, there's a bunch of things that are legal, but not everything that's legal is a behavior you necessarily should do, some people might say. So somebody can be a model for these type of behaviors. Are there any other thoughts about this? There's almost like Martin Luther King Jr., for example, in contrast with Karl Marx. So I will leave that there. So that's, so right. You can connect to thinking about how these different, very iconic individuals were viewed by followers. Are there any other thoughts about this term model citizen, or why? I mean, I guess what I want to push you to think about is, okay, great, but why? Why should I vote? Why should I wear a mask? So are there other ways we can use the term model to help sort of be related to that? Like so far, you're just saying, that somebody can model good behavior, but how do we know it's good behavior? Or are there any other thoughts on how we can use this term model in model citizen? I like to use the example of the stoplights. We can say a model citizen stops at all red lights. And you can say, okay, that's fine. So a model citizen stops at all red lights. So if I am modeling good behavior, I'll stop at red lights. But then you'd have to sort of say, but why the heck do we stop at red lights? So what? Why should I be somebody who stops at red lights? Because then we haven't thought about that. So laws, right? You can put laws in place. So laws kind of codify these model behaviors. So when a behavior we view as really important, we just make it a law, right? But still, why did that behavior become a law? Why is it important for us to stop at red lights? Is it just because somebody said it's important? I see in the chat, protection, right? So we have a model of the way civil society crashes, right? Civil society operates on assumptions about behavior. I assume, like right before this, I had an appointment. I thought I might have, I had to rush back here to make sure I wasn't late, and I had to drive in traffic. And I am confident that if that everyone else is going to be stopping at the red lights, and that gives me the confidence that if I drive through the green lights, and game theorists call this a correlated equilibrium, is that if I know that everybody's stopping at the red lights, then I can drive through the green lights without worrying about those people deciding to run the red lights. And so I, this model citizenry is a set of assumptions that we actually use in order to sort of say what we view, how we view society should run. So the idea being here is that if the claim here is that what if everyone stopped at red lights? Well, then we claim that people should be able to safely drive through a city. If we happen to go into an area where people don't stop at red lights, that doesn't work anymore. So part of the reason we have model citizens, a model citizen basically is a prescription for behavior that if everyone were to behave that way, our society would function in a way that we've deemed desirable. And so, for example, a model citizen votes. We know that not everybody votes. Even in the past presidential election, where a lot of people voted, not everybody voted. So in our society, it plugged right along. So, but in a ideal version of society, in the model society, the model citizen votes. And we can then write, political scientists can then say, well, in such a model society, if everyone votes, these are particular outcomes we would get. And we can make claims about those outcomes actually being fair, for example, being equitable, et cetera, et cetera. And all of those claims about these democratic outcomes would lean upon the assumption that everyone's going to vote. So a model citizen votes. Exactly how many people have to vote for us to get close to our model society is an interesting question. And that goes back to that George Box quote about all models are wrong, but some are useful. And the question is, how wrong do they have to be to stop being useful? We know that we're never going to get everyone to vote. But if we get enough people to vote, we hopefully will get an outcome that will be close to the model outcome in this sort of hypothetical world where everyone votes. So a model citizen, I claim, a prescription of behavior that if everyone did that behavior, we would achieve our societal goals. So that's the what if question. What if everybody acted that way? Now, the other thing that I want to point out to you about models is that models have this so-called GIGO property, garbage in, garbage out. And so the idea here is a model is only as useful as its assumptions are realistic. And so the idea here is you can say, yeah, it would be wonderful if everyone behaved a particular way. I have these discussions with my wife all the time where she says, I don't understand why people do this particular thing. If only they would not do this particular thing. And in the end, it's like, well, that's fine, but we're never ever going to get them to not do that particular thing. And so we have to find a way to live in a world where people don't, do that particular thing. So if we assume that everybody does something that they don't, then our computer model might look beautiful, but that beauty that's in the computer model will have no relationship to reality because the hidden assumption in our computer model that everyone was going to behave a particular way is flawed. And this brings me back to the fashion models. That jacket, no matter how good it looks on him, if he is not a good model for me, if that assumption that the jacket is going to go on someone that looks like him, if I don't look like him, I can't count on that jacket looking good on me. And so that's what I mean by garbage in, garbage out. A model itself, the idea of putting a jacket on a human is a beautiful one. I love that idea, but you got to pick the right humans. It would be nice to have 4 or 5 humans. So here's a black human. So here's a brown human. Here's a white human. Here's a heavier human. Here's a lighter human, and mixtures of those. And given that, put the jacket on all of those. and then let me pick the one where the assumptions best match my target scenario. And that is going to work best for me. But if you only give me one picture there, then no matter how great I like that picture, it's not going to look good on me. So that's what I mean by the GIGO property. But ultimately, we've got to be careful about how much of a need for realism that we look for, because in the end, no model is totally realistic. Essentially, all models are wrong, but some are useful. The practical question is, how wrong do they have to be to not be useful? That's the George Box quote, or George Box quotes. So ultimately, by the end of this class, you shouldn't be building computer models where you add every single tiny little nuance in of the system, unless you really think you need that nuance of the system. Because eventually, every little nuance that you add in is actually room for your model to become less generalizable. And you might accidentally make the wrong assumption for one of those. And even though you thought you were making it more realistic, you're gradually making it less realistic. So often the best models are the ones with the fewest assumptions. The best models are often the ones that are almost the simplest, the most naive, because they're the most generalizable. And so that's kind of where we're going there. So that was kind of a summary of where I want you to be after that lecture. And we'll close with a couple of other examples and mental models here. And then that will then allow you to do this homework assignment, which is a pretty quick one. All right, so any questions about that, about these basic ideas of what a model is? Oh yeah, Morgan, sorry.
So I heard you said usually the models that work the best are the most naive ones. And I've seen this like in plenty of cases, but I'm curious if they use those models without the least amount of assumptions, then how can they know that it's going to apply to the general public or not for like certain
I mean, that's a good question. So I guess the idea is how realistic you need your model to be. And we're going to talk about this as we go into next week. There's a process of model building, and this relates to this iterative process here, where we often start with a simple generalizable model, and then we keep adding more specific details as we tailor it to a particular system. So I will use the example of the game of Monopoly. The game of Monopoly is a model for how real estate works in any city. And it tells me things that will hold in Los Angeles, as well as it'll hold in New York City, as well as it'll hold in Columbus, Ohio. But when I actually want to get into the real estate market and all the, these nuanced little details, the game of Monopoly becomes far too trivial for me to actually implement a business plan in New York City, Columbus, or Los Angeles. At that point, I definitely need to add all those details in. But if I'm just trying to understand basics of how real estate works, then it's actually going to overcomplicate things if I bring in all of the municipal laws of New York City to somebody who's never going to become a real estate broker in New York City. They're going to work in Columbus, Ohio. And so the person who works in Columbus maybe actually would do better off with Monopoly than they would with a accurate model, a precise model in New York City. Does that make sense? Great. Any other questions? All right. Okay, well, let's do a quick attendance exercise, just keep everybody awake. And this one's an easy one. I put the link, by the way, in the chat. You can also get the QR code here or type it in yourself. The question here is, what is the question that a generic model seeks to answer? And so just drilling this thing into your head, basically smash that link, go to the form, fill it into the question one answer there, and then let it sit. And we'll submit at the end of class because there might be another one of these or two. All right.
I think there's something wrong with the link.
Oh, again, I typed it. That was my fault. I did the same thing last time. I keep typing 202. I don't know why I'm doing that. It's 212 ATT. So it's bit.ly/212, like the class, ATT, like attendance. So if you click on the link in the chat, it should bring you to the right one. I apologize for that. All right. So, all right, kinds of models here. So I'm going to kind of speed through a little bit of this, but I basically, a lot of these are, I want you to recognize your mental models. And this is kind of going to be the subject of the homework that you'll sort of formally assign today, homework assignment A2. And it is, if you look at this, my guess is that your brain immediately starts telling stories. Again, my pace this semester over Zoom is a little slower. I would normally do kind of a classroom exercise here where I'd ask for some of these stories that you guys would be coming up with here. And whenever I do this across many classes where I teach about modeling, I hear someone talk about Pac-Man, for example. How many people, just with your reaction button, see a Pac-Man narrative when you stare at this picture? Anybody? So you look at this and you're nobody. I got nothing. So with you, okay, so at least they do see the Pac-Man. I don't know, someone told me that, actually told me a whole thing about these 3 angry Pac-Man were actually after a hidden, and I think she even said a hidden princess who was hiding underneath a white triangle, and they were entering a room trying to find her. Like, it was this elaborate thing where, like, it's just a couple of lines on a page and the brain immediately went there. And it's that your mental models are always trying to make, trying to answer causal questions about data that you see in the real world. You might see 3 circles here. There are not any circles in this diagram. This shape here, you would say, no, it's a circle with, it's had a wedge taken out of it. Well, that's fine, but it's not a circle, and there's actually no wedge here. Like, this is just white space. And yet we assemble stories where we say, well, there's actually a triangle with black edges, and then there's a totally white triangle set on top of it, and there are these 3 circles, and those are set on top of that, and that's what makes this picture. And so on and so forth. A lot of people say they see the Star of David, for example, as if this shape here were continuous, when there's no continuous perimeter around this thing. So your mind is using mental models to answer what if questions. What if I came about this in real life? Well, that would mean that this particular thing happened. That's evidence that this particular thing happened. Similarly, if you look at this cartoon, you might immediately say that there's I've heard stories where students say, like, well, there's a really arrogant individual who is standing on a wooden floor, and someone who is upset at that arrogant individual is cutting out a circular hole around that, in which case this arrogant individual is going to fall through that, perhaps to his demise. And I think if I were to say that, a lot of you might say, yeah, I can see that. But if you really drill down like a computer would into what you see here, we see that, for one, this doesn't even look like a human being. This is, I have a relatively large nose myself, but even my nose doesn't compete with this thing that's out here. This head is extremely small. There's no way a human brain would fit. The proportions are all wrong, but we all accept that we have a mental model of what a human is, and that mental model is what we're using to make sense of this diagram. Likewise, this here you might think is a circle, but if I actually were to go and measure the width here and the depth here, I see that actually it's an oval, and but I have a mental model that says that well, a floor, when it's tilted a particular way at a particular perspective, it makes circles look like ovals. So I am going to assume that actually what's going on is that there's a circle there. So you're filling in all these gaps with your own experience in your head in order to try to make sense of these data. And that's something that you're just adding on your own. Likewise, so over here on the left-hand side here, this is kind of a famous painting. I think you can find it in the Louvre, where it's, this in French, I think it says tandem convergent. This is the model for fiancés. Tandem divergent, the model for a couple that is just about to get divorced. And so when you look at these things here, you know that these bicycles, these are bicycles. There's nothing about relationships here. There's nothing about love or heartbreak. There's nothing about passion. And yet, at least me, I look at these, I get it. Like this here communicates to me, what if as I was in a particular situation where I was so in love with someone that I only wanted to get closer to them, and I could not get any closer to that person. That's what's being captured here with these bikes. These bikes, no matter how much you pedal, these bikes can't get any closer. Similarly, if you're trapped in a marriage with someone that you don't want to be with, then you might want to be as far apart from that person as possible, but you're stuck. No matter how hard you pedal, you're stuck in the same structure here. I don't need to build these, although someone actually has built them, to be able to answer a question of, will these bikes work? These bikes, these are metaphors that help me, think about something that has nothing to do with bikes. But if I wanted to think about bikes, I immediately understand them because I have a mental model of how a bike works. Likewise, you might have mental models of how boats work. So you might think about, if you are back here and you've got this rudder back here, and you might think about the first time you ever were to go into a boat, like a fishing boat like this, and try to drive it. You'd say, well, if I wanted to turn left, what would I do? And in your mind now, you might say, well, if I want to turn left, I might actually want to pull that rudder on this side right. And so, but initially, the first time you're in that boat, you might have tried experimenting with actually going, pushing it left first, because you figure, okay, I push the rudder in the same direction as I want to go. And when the boat goes off in the other direction, you update your mental model. So you have a mental model for what if I were to move the rudder left or right now. And you start out maybe with the wrong model. If you ever watch Independence Day, now an old movie with Will Smith, he's in an alien vehicle and somebody's taped to the steering wheel of this vehicle which direction to push it for the throttle to go forward or backwards. And they actually had arrows on it, and they drew the arrows the wrong direction. And he wants to go out, and he pushes down on the throttle because that's what it's said to do, and it goes back into the dock. So instead he says, some jerk, he flips it around, updates his mental model, pulls back, and heads out perfectly. So you have these mental models for what if I was going to do this thing. It's backed up by your experience, and you're constantly updating them. They're being updated over 20, 30, 40, 50 years of life, constantly learning how to operate in the world. Now, those mental models sound extremely powerful because of how long they've accumulated. But I also want to challenge that part of the reason we have this course is because mental models can be extremely flawed. So this is a scenario that I like to give here. This is a classic one from modeling courses, and how people respond to this scenario. People have studied this over years. And so you most likely will have a different feeling for this than someone who were to take this class in like 1970. So the scenario here, if you haven't read it, is a man and his son are driving in a car one day when they get into a fatal accident. The man is killed instantly. The boy is knocked unconscious, but he's still alive. He's rushed to the hospital and will need immediate surgery. The doctor enters the emergency room, looks at the boy and says, I can't operate on this boy. He is my son. So what's the answer here? How is this possible? What do we know about the doctor based on this? Or is this a paradox? Does anybody have some guesses they can put into the chat of different things? I see a couple of guesses. I'll let a couple more come in. Any others? All right, so far I've gotten, okay, now I'm seeing a couple others come through. Yeah, so I've gotten, a couple of answers came in. What if the doctor's a mom? Doctors can be women. Why can't it be the mom? What if the doctor is male and gay? So if just because someone has a son doesn't mean they have to have heterosexual parents. And then there's some other things here as well. Maybe the boy has a name, like there's these kind of things that get a little bit more out on the fringe about a non-traditional name for the boy, and so on and so on. And so what's interesting to me is that sort of older audiences, when they read this scenario, could not make any sense of it. If you ask an older, even today, if you ask people of a certain age, they'd say that doesn't make any sense. And because they have a weird mental model of what it means to be a doctor. Younger audiences, I've asked this question to a bunch of students over the last couple of years, and people say there's a lot of ways this could happen. So what's the problem? Why are you even bothering with this? This tells me more about you, Ted, than me. The fact that you're even bringing this thing up. And so it just goes to show that and what I think is kind of interesting is that when I example for you, I would get mom. Recently, I've gotten several people that on their first answer would say that the doctor is gay, and I've had some classes where that was the only answer, and that has been fascinating to me, because when I would ask this question years ago and students would give me the mom thing, I'd say this is great because it really shows that students coming through the system now, we live in a world where it is totally acceptable that women and men could be these professional positions, doctors and whatever. But it's been interesting to me that now that once the answer about a gay doctor dad became a possibility, I've actually been, now when I ask this, because I asked this in multiple classes, I actually have gotten fewer answers about the mom. So it's almost like with the rise of non-traditional sexual lifestyles, there's been somehow a recession in gender roles, which is sort of weird, at least based on this little anecdotal experiment here. So I don't know, but that's just kind of a side note. But my point here is that it's the same text, but all of you can interpret it differently. And so your mental model is what fills in the gaps here. So all models are wrong, or some are useful. How useful is your mental model here? My hope is that your mental model is a lot more useful than some, random 75-year-old who you pick up off the street. Because there are definitely real scenarios where this could occur now. So that's what I'm hoping you're seeing of it, that in mental models here, their major strength is they're a tremendous storage, but their weakness is they're unreliable in handling complex dynamic change. And so when you're trying to ask somebody, where a particular object is at an instant, well, it's going to be there. If you cover it up, it's still going to be there. I have a mental model, it'll understand that. But if I throw the ball and ask you where it's going to land, it's a little harder to deal with that. That's that dynamic change of trying to figure out where the ball is going to land. You don't know what the ball is made of, or how it feels, or how hard I'm throwing it. And even if you did know those things, you still might have a hard time guessing exactly where it's going to land. In just general custody, the fact that in order to understand that hospital situation there, you have to know a lot about what type of society we're living in. What are the demographics of people who are in the profession of emergency room doctor? And so that becomes much more complicated for mental models to work through. So when we're thinking about complexity, then what we try to do is take all of the good stuff from our mental models and formalize it into quantitative models, because quantitative models are much better at doing things like dynamic change and interconnected webs of things. But we just have to formalize things first, and that's the challenge, and that's what we learned to do during this class. Their weakness is that they lose information. And so once you formalize those things written down, you may now have said, that model that you've built may now only model Columbus, Ohio. It doesn't model Los Angeles anymore, now that you've customized it for the parameters of Columbus, Ohio. So those can be the weaknesses. But also, there's a communication problem here. Like this model here, which is a model of disease spread, where S dot, that's like ds, dt in calculus, like it's kind of hard to go into a room full of fourth graders and tell them how COVID works if all you got is this thing. So what are the uses of quantitative modeling? I've kind of hinted at some of these. Inference is one of them. So in prediction and narrative. And so in prediction, that's the case where we have weather models. And so you give me data about the weather as it's been today, as it's been the last couple of weeks, and I will then predict how it'll be tomorrow. And so that's really hard for our mental model to do. But if we have a good quantitative model, it can help us predict what's going to happen. The other thing we can do with models is inference. So inference is when we take data and then we want to infer what's going on behind the scenes with that data. So we took data on high school GPA, university GPA, and then in that particular case, we'd like to infer what is the causal link between high school performance and university performance. And so we can, based on the data that we gathered, then that model ends up helping us make inferences on certain relationships. And so that is, so inference is when you're mapping from data in the real world to a guess of what's going on. So is high school GPA informative against university GPA? These data, once I draw that regression line, because this regression line is, has a slope that's not horizontal, that suggests to me that is some relationship between these two. I don't quite know exactly why there's a between those two, but I now can make an inference that there is a relationship between those two I'm looking at. So you're inferring something from data. The other thing that we do with these models is, and it says my internet can be stable, hopefully that's resolved. The other thing we do with these models is stories. And so sometimes it's harder for me to tell a story without a graph. There's a bunch of times where I think, people have probably asked you to explain something and it's easier for you to draw it out. Back when Obama was president, there was a major downturn in the economy and he put together a recovery plan. So he wanted to communicate to people what things would be like with and without the recovery plan. And so they built a model that was meant for narrative. It was meant to convince people that the recovery plan was worth it. And this model here had on this x-axis, and it had the unemployment rate on the y-axis here, and they modeled what happened without the recovery plan, and then what would happen with the recovery plan. And the whole point of this was to convince people gap between here, the reduction in the unemployment rate between the without and the with, worth it to consider the recovery plan. It's telling a story. We're not learning something about the world. We are using a quantitative tool to show me the numbers to try to make a more convincing argument. Likewise, a lot of people do this with CO2 and temperature. But you have to remember, models can be misused. If I take this CO2 and temperature chart here, where global temperature, that's the kind of the jagged red line, and CO2 at two different areas on the planet is the green and the blue line. We see that CO2 tends to predict this temperature here. If I was to just zoom in on a small section of that, I'd actually see that although CO2 is going up, temperature is staying flat or maybe coming down. So you can misuse these models to manipulate people when telling. So if you tell the full story, where you look over many, many decades or centuries or longer, then you get a very different picture than when you zoom in on a particular decade. And so models can be manipulative in that they can appear to be convincing because they're numerical, even though the assumptions, the garbage in, garbage out, the assumption here is that these decades were typical. And apparently, if I zoom out, I see that these decades are not typical. So that was the garbage by choosing those particular decades. All right, so I don't want to spend a whole lot more time on this, but I do want to at least mention that when you hear the word model and quantitative model, people are either going to mean a mathematical model. We've talked a little bit about this. This is kind of the sort of stuff you started dealing with in your first calculus course. Mathematical models are great because they provide exact solutions and relationships, quantitative relationships that something is exactly 4 times something else, but they're really hard to sort of understand unless you're a specialist. And they often only give you answers in scenarios, like out at time goes to infinity, for example. An alternative to that is to use so-called numerical methods, where you still use complex mathematical models up here, but instead of trying to solve them with calculus, you then do what is referred to as just sort of as as taking the equations here and solving them numerically, which just means basically instead of looking for a mathematical expression as a solution, you look for a graph as a solution. And this gets closer to what we're doing in this semester, but we're kind of kicking out this ugly mathematical expression here, because once I build a mathematical model like this, it's difficult for me to make modifications to that model. So instead, we use simulation methods where we build models that look a little bit more like this one here, where they're formulated as these kind of structures where we understand the small scale structures, and a computer program helps us link all of those together. And it then manages the math behind the scenes so that we don't have to. And that managing of the math behind the scenes and then executing that math is what we're calling a simulation. And it gives us graphs out. There's no hope of getting mathematical expressions out, but the graphs we have are like simulated data from a hypothetical world. And that's kind of what we're doing here. There are different types of simulation methodologies. There are other courses on each one of these, like agent-based modeling. There's another sustainability course that goes into that. There are courses that use in engineering and business on discrete event system simulation. We are doing so-called system dynamics modeling. I don't really have the time to go through all the differences here, but my focus here is that I just wanted to tell you that this semester we're learning one of these. You might go into other courses later where you talk about simulation and you might not recognize some things, and that's because there are other types of simulation as well that you use for different applications. And that's all that I'm kind of getting at here. And so our focus in this semester was using system dynamics models, simulation models, to explore how causal structures lead to dynamical patterns. So when you see oscillations in real data, what possibly could be causing those oscillations? Those are questions we would like to answer. When you see growth in real data, you can sort of answer, well, why would this possibly appear to be growing forever and not oscillating? Those are the types of questions that we like to answer with the models that we'll build this semester. And I'll pick up for questions after here. So we didn't really have a lot of time to start on this little assignment, but this assignment is easy to do at home. It's just another one of these where I ask you 3 questions about your personal mental models. The other things you should be doing is do your reading exercise 00 that unlocks the rest of the course. There's a muddiest point assignment that's due Sunday night, and then start reading chapter 1. There's a perusal assignment, a reading exercise, and the reading assessment, and those are all going to be due before Tuesday. So do the reading and the exercise by Monday night, and do the reading assessment before Tuesday's lecture. And the assignment you're going to do is just, you're going to answer a question about this graph, you're going to answer a question about this graph, and you're going to answer a question about this scenario. And I'm just interested in hearing your kind of mental model, bringing up those mental models. So with that, I don't want to keep you any longer. Here's the attendance question today. And so we're going to do one last attendance question. And that question is going to be, what is the strength of mental models? So what is the good part of mental models? And that's all I've got for you today. Sorry that I ran a couple minutes over. If you have any questions, I'm happy to stick around. Otherwise, that's all I've got for you. Thanks for the feedback in the chat. Appreciate that. And thanks for saying, thank you, or saying a lot of, in the engineering classes I teach, they just log out. But in all the sustainability classes I've taught, people always say something as they leave. And it's nice. Appreciate that. So thanks. Thanks. All right, looks like we've got kind of an anti-quorum here, so I'm going to go ahead and end the meeting. So have a nice weekend and see you next week.